Hello everybody, we're getting ready to do lesson 11.4 part 2, pre-calculus math today. And for today's lesson you have 6 points that will go into your notebook or your notebook sheet, and 46 points that will go onto your classwork sheet. Have those ready to go. And put your name, date, period here, students. And then onliners, homeschoolers, make sure you put your due date here. And today's bell work, students and teachers, today's bell work. Sketch the graphs of y for here, 73, this is 74, and each transformation, these are your transformations, so graph this and graph these, sketch them over here. And on the same rectangular coordinate system, so sketch those here, and then down here, find the sum. And see you in 5 minutes, students and teachers. See you in 5. Okay, welcome back everybody for today's solutions for the bell work. And for 74 up here, you have y equals x cubed and all these other shifts here of the y equals x cubed function. X plus 2 cubed, 2 minus 1/4 x cubed, 3 plus x cubed, 3 times quantity x plus 1 cubed. So all those shifts would be here. Here's A here, the x plus 2 cubed. And then B would be the 3 plus x cubed, which is right here. That would be your 3 plus x cubed. And then C would be the 2 minus 1/4 x cubed, and then the D would be here, the 3 times x plus 1. So let's see, the D here would be this one here. That would be your D for your graphs, your sketches. They should look something like that anyways. And then down here for your summation, we have 0 plus 5 plus 20 plus 45 plus 80, which is 150. You have 0 through 4. Substitute in for I, and then you get this summation down here. Into today's lesson, we start with a notebook entry. Limits at infinity for rational functions. Consider the rational function f of x equals n of x over d of x, where n of x equals a to the n, x to the n, plus ... plus a to the naught, and d of x would equal b to the m, x to the m, plus ... b naught. Meaning we start with a, we have descending exponents there on each one of these parts of this rational function, your numerator and your denominator. The limit of f of x as x approaches positive or negative infinity is as follows. So as x goes to negative infinity, the limit of that f of x equals 0 if n is less than m. So if n is less than m, and a to the n and b to the m, if you both of these, if n equals m, in this case here, where your degrees equal each other, then these would approach infinity here when that happens. If n is greater than m, then the limit does not exist. So if the degree of your numerator is larger than the degree of your denominator, then the limit does not exist. Okay, moving on into our example 3 here, finding the average cost. You are manufacturing greeting cards that cost 50 cents per card to produce. Your initial investment is $5,000, which implies that the total cost C of producing X cards is given by C equals 0.50X plus 5,000. The average cost per card is given by average cost equals C over X, which equals 0.50X plus 5,000 over X. Find the average cost per card when A, x equals 1,000, B, x equals 10,000, and C, x equals 100,000. D, what is the limit of C as x approaches infinity? Okay, for A, in this situation here, when x equals 1,000, the average cost per card is, here we go, we plug in up here, 0.50 times 1,000 plus 5,000 over 1,000. So x equals 1,000. When we do that, then our average cost will be $5.50 per card. And then for B, when x equals 10,000, the average cost per card in this situation here, 0.50 times 10,000 plus 5,000 over 10,000. That would equal $1 when you print off 10,000. And then when x equals 100,000, the average cost per card is, average cost for 100,000 cards would be 50 cents. So here would be your graph here of this cost function for manufacturing these greeting cards. So here is average cost C equals C over X, which equals 0.50X plus 5,000 over X. And then this will be your cost function here. As X approaches infinity, the average cost per card approaches 0.50. 0.5 would be this asymptote here, horizontal asymptote. Let's try one. The cost function for a certain model of a personal digital assistant, PDA, is given by cost equals 13.5x plus 45,750, where C is the cost in dollars and X is the number of PDAs produced. Write a model for the average cost per unit produced, and then B, find the average cost per unit when X equals 100 and X equals 1,000. So up here, write a model for average cost per unit produced. So when we do C of X here, we get 13.5 X up here plus 47,750 over X here. So we're canceling out this X here. We get a C of X here. So that would be your average cost function here for this situation here. And then now we plug in for 100 and 1,000. And that's up to you, students, to do that. So get on that now. Limits of sequences. Limits of sequences have many of the same properties as limits of functions. For instance, consider the sequence whose nth term is a to the n would equal 1/2 to the nth power, 1 over 2 to the n power, where we have 1/2, 1/4, 1/8, 1/16, 1/32. As n increases without bound, the terms of this sequence get closer and closer to 0, and the sequence is said to converge to 0. Using limit notation, you can write the limit as n goes to infinity of 1 over 2 to the nth power equals 0. The following relationship shows how limits of functions of x can be used to evaluate the limit of a sequence. Limit of a sequence. Let L be a real number. Let F be a function of a real variable such that the limit as x goes to infinity, f of x equals L. If a to the n is a sequence such that f to the n equals a to the n, for every positive integer n, then the limit as n goes to infinity of a to the n would equal L. A sequence that does not converge is said to diverge. For instance, the sequence of 1, -1, 1, -1, 1 diverges because it does not approach a unique number. So let's take a look at a few. Finding the limit of a sequence. Find the limit of each sequence. Assume n begins with 1. So a to the n equals 2n plus 1 over n plus 4. So if we take n to infinity here, we will eventually get 2 as our result of that limit. So we have 3 over 5, 5 over 6, 7 over 7, 9 over 8, etc. So it would be 2n plus 1 over n plus 4 here. So if we double n up here, and then we add this, and then we have n down here, it will come out to be equal to 2 eventually. If you take that to infinity, 13 over 10, it will eventually come out to 20 over 10 is what it would be equal to, or 2 in this case here. If you look at the graph of that, it would eventually amount to 2. And then we have b to the nth equals 2n plus 1 over n squared plus 4. In that situation, if we take n to infinity, we have 2n plus 1, and we have n squared, so our degree down here in our denominator is larger than our degree in the numerator. So this would be a 0. This would amount to 0 here. And so this eventually gets smaller and smaller and smaller. And then up here, c to the n would equal 2n squared plus 1 over 4n squared. In this situation, this would equal 1/2, because we start out with 3/4, 9/16, 19 32nds, etc., until we would eventually equal 1/2 would be the horizontal asymptote for this one here. And if you look at the graph of that, you could definitely see that. 1 over 2 here. These two have the same degree, so that's really what's going to count here as you go to infinity. Okay, let's try one here. Write the first 5 terms of this sequence here and find the limit of the sequence if it exists. If the limit does not exist, explain why. Assume n begins with 1. So for this one up here, a to the n equals n plus 1 over n squared plus 1. What we have here is we start with 1, and we go as we increase, we get 3 over 13 here. It eventually will equal 0 here because our degree in our denominator is greater than the degree in the numerator. And students, this is on you, so start that one. Finding the limit of a sequence. So find the limit of the sequence whose nth term is a to the n will be 8 over n cubed, and then inside brackets n times n plus 1 times quantity 2n plus 1 over 6, close bracket. Begin by writing the nth term in standard rational function form as the ratio of 2 polynomials. So 8 over n cubed, our expression up here, here's our original nth term. And then we're going to write original nth term in a different way here. We're going to multiply these two together and then multiply through here with 8. And then we're going to multiply our fractions now, 8 to the n. And then we're going to write this in standard form now. So if we multiply these two together, then multiply through by 8n times the multiplication of these two binomials, we'll get 8n cubed plus 12n squared plus 4n over 3n cubed. From this form, you can see that the degree of the numerator is equal to the degree of the denominator. So the limit of this sequence is the ratio of the coefficients here, 8 over 3, of the highest terms. And in that case, it's 8 over 3. So that would be the limit of this sequence would equal 8 over 3. A numerical solution for that, enter the sequence here, this sequence, into a graphing calculator and create a table, be sure the graphing calculator is set to sequence mode. Now, if you have that set to sequence mode, you can estimate that as n approaches infinity, a to the n gets closer and closer to 2.667 or 8 over 3. So here's your 2.667, and then here is your graph of that right here. And this would be your horizontal asymptote, 8 over 3. So that would confirm what's in the table there. So let's try one here. Use a graphing calculator to complete the table. You need to complete that table and estimate the limit of the sequence as n approaches infinity. Then find the limit algebraically. So the table would have these values here once you put this into your calculator. And then the rest of it, I'm going to let you do that, students, and find the limit algebraically. I'm going to let you do that here, students. Find that algebraically. And that was 11.4 Part 2 Pre-Calculus Math lesson. Animated PowerPoint Math Video at AOL.com for questions or course materials. Thank you very much.